Strong force fields. Now let us return to the force that holds the nucleons together in the nucleus. The only forces known in 1934 were gravity and electromagnetism, but gravity is not strong enough and the electromagnetic force produces repulsion, not attraction. Clearly, there must be a new force acting within the nucleus and it must be strong enough to overcome the electrical repulsion. It is called, therefore, the strong nuclear force or just the strong force. A short-range force. The real puzzle about the stronger force was not its existence, but its short range. If it fell off according to the inverse square law, like gravity and electromagnetic forces, it would be observable outside the nucleus, but it is not. A further indication of its short range is the fact that the binding energy amount of energy needed to break up the nucleus decreases in heavy nuclei. This shows that the binding forces between nucleons are not cumulative, and this can only happen if the range is small compared with the size of the nucleus. Because of the success of Maxwell's electromagnetic field theory and the acceptance of gravity as a field, there was no doubt in anyone's mind that a strong force is transmitted by a field, but no one was able to come up with the right field equations to describe this new short-range force. The answer came from an unexpected quarter. Enter Japan. Up to then, theoretical physics had been mostly an European activity, dominated particularly by Germany and Great Britain. The United States was still lurking on the edge and other areas of the world were completely dormant. As for Japan, it had maintained its ancient culture in isolation from the West until 1853 when the Commodore Perry and his US Navy warships entered Yokohama harbor. This invasion led to the fall of the existing shogunate and a major restoration. During the ensuing Golden Age, many Japanese went to Europe to learn about Western science and Westerners were brought to Japan to teach. Never had a country accomplished so much so fast, and today Japan is one of the leading countries in the world in both science and technology. Hideki Yukawa, son of a geology professor, graduated from Kyoto University in 1929. 5 years later, as a resurgent militarism was engulfing Japan that would culminate in the invasion of China in 1937 and the attack on Pearl Harbor in 1941, Yukawa came up with the answer to the nuclear force quandary that had stumped Western scientists for over 20 years. The Yukawa field, as it is sometimes called, joined the ranks of the gravitational and electromagnetic fields as the third fundamental force field in nature. The Yukawa field, starting from the analogy with Maxwell's equations, Yukawa developed a field equation that contains a new term that changes the force from a slow varying one, like EM and gravity, to one that falls off rapidly, in fact exponentially. The new term contains a constant that he called lambda, and by choosing lambda properly, Yukawa was able to make the theoretical range of the strong force match the experimentally determined value. Yukawa thereby did what Maxwell had done with electromagnetic forces. He started with a force that was understood less well than electromagnetic forces and devised field equations to describe that force. Color it purple. I choose purple as the color to represent the strong field. Around every proton and every neutron I ask you to picture a small purple halo representing the strong fields. Unlike the green of the electromagnetic field and the blue of the gravity, this halo doesn't extend very far, but nevertheless it is there. In Chapter 6, we will learn that the orbiting electrons shown in the figure are really fields, and this will add yellow to the space around the nucleus. These fields all exist independently and do not combine with each other. The same atomic nucleus shown in the figure with its surrounding green like EM fields, but with a purple halo added to represent the short-range strong field that extends a short distance outside the nucleus, not to scale. Yukawa's quantum. Yukawa realized that just as EM radiation is made of discrete quanta called photons, so a strong field could exist as separate quanta. And just as photons are described by Maxwell's equations, so the propagation of these quanta would be described by the field equation he had derived. This is where Yukawa came up with his second surprise. The lambda term that he added to give the field a short range also affects the propagation of a quantum, causing resistance to changes. A field with mass. In classical physics, mass or inertia is the tendency of an object to resist a change in its motion. Thus, while photons and gravitons travel at the speed of light, the lambda term would cause Yukawa's quanta to propagate through space much more slowly, in fact, like a particle with mass. When Yukawa calculated the effective mass of his field from the experimentally determined lambda, he found a value about 200 times larger than the electron mass, but less than the proton mass. Because of this, the strong field quantum was given the name mesotron, from meso, meaning intermediate, later shortened to meson. Until 1935, it was thought that only particles with zero mass, such as photons, could be the quanta of a force field. Yukawa showed that this is not so and that particles, now called mesons, could also be the quanta of a force field. That Yukawa should have arrived at this important discovery before any of the European and American physicists did is all the more remarkable when one realizes that Yukawa had very little contact with European physicists. A field with a charge. Mass was not the only surprise that Yukawa found. In order to exert a binding force between protons that are positively charged and neutrons that carry no electric charge, the new field must itself carry an electric charge. In fact, there must be two charged fields, one positive and one negative. A third field with no charge was added later. Up to this point, fields were properties of space whose only physical manifestation is that they exert a force. But now physicists had to cope with a field that has both mass and charge, properties previously associated only with particles. To those learning physics for the first time, it may not be a surprise to learn that fields can have mass and charge. After all, if everything is made of fields, then all physical properties, spin, mass, charge, energy, must be properties of fields. But those with prior exposure to physics have come to see those properties as belonging to a solid matter. So picturing them as properties of an intangible field may not be easy, as all we can do is point to a term in the field equation that slows propagation of the field and hence corresponds to mass, and points to an interaction term that describes how the Yukawa field interacts with the electromagnetic field, giving it an effective electric charge. It is these mathematical terms in the field equations that give the field the mass and charge properties that we ordinarily ascribe to material objects. A field without spin. Although the strong field has mass and charge, in another respect, it is simpler than the electromagnetic field. We recall that quantum fields have a property called spin or helicity that is related to the internal complexity, and that the electromagnetic fields with electrical and magnetic components that can point in various directions has a spin of 1. Well, the strong field does not have the same complexity. Its force is always attractive and its spin is zero. Now can you hear some of you screaming, "Wait a minute, the gravitational field also consists of a single attractive force, and yet you said its internal complexity is greater and its spin is too." This is true. For some reasons that are beyond the scope of this book, Einstein's gravitational field is more complex than any other field. I must ask you to take it on faith that the strong field is simpler than both the gravitational field and the EM field, and its spin is zero. Field or particle? Yukawa's field with mass and charge further narrowed the difference between fields and particles. After all, if a field quantum is emitted as a unit from a single location, like a particle, it is absorbed as a unit at another location, like a particle, and in between exhibits a mass and an electric charge, like a particle. How is it different from a particle? There is no empirical test that can answer this. The difference lies in how we choose to perceive reality. The picture in our mind, and this difference is immense. A particle is a localized bounded object. It has edges, or perhaps as some think, it is only a point. A particle exists in space, and around it is empty space. And a field, on the other hand, is something that exists everywhere as a property of space. Its intensity may be small, but it is never zero. Even in eras where there are no quanta, there is a small amount of field called the vacuum field. In QFT, there is no such thing as empty space. While particles move through space like baseballs, fields are diffuse and spread out. They exhibit interference and diffraction. Nevertheless, when a spread-out quantum is finally absorbed, it collapses into one location. See quantum collapse in Chapter 10. When Yukawa's theory came along, the particle picture was strongly embedded and QFT was in its infancy. Even the long-held view of light as a field was doubted, when most physicists following Einstein in his belief at the time that photons are particles. And so Yukawa's meson was seen by most physicists as a particle. However, Yukawa himself was careful to use the term quantum. The term Planck was introduced to denote a discrete amount of fields. While I have been using the word particle in accord with custom, please understand that these particles are really fields, or I should say quanta of fields. In QFT, there is no such thing as a particle. Where is it? Whether it is a quantum of field or a particle, Yukawa had predicted a new entity, something not previously seen or even dreamed of. Why, wondered Yukawa, had it not yet been seen? As such a quantum with large mass and positive or negative charge has never found by experiment, the above theory seems to be on a wrong line. The reason why such massive quanta, if they ever exist, are not yet discovered may be ascribed to the fact that the mass is so large that the necessary energy relationship is not fulfilled in ordinary nuclear transformations. Yukawa. In other words, Yukawa's quanta had not been observed because there wasn't enough energy to create one. While photons can be created with very little energy, for example by heating up atoms to create a field quantum with a mass 200 times that of an electron would take more energy than is found in an ordinary atom. Even radioactive nuclei do not have enough energy to create such a massive particle. This led Yukawa to make a prediction that in its audacity rivals Einstein's prediction about the bending of light. These massive quanta may also have some bearing on the showers produced by cosmic rays. Yukawa. Like Einstein's famous prediction, Yukawa's was eventually verified, but the path to verification was not as quick or direct, and it involved one of the most famous false positives in physics history. To understand the story, we must first understand cosmic rays. Cosmic rays. Cosmic radiation was discovered in 1912 by the Austrian physicist Victor Hess. Like many discoveries, it was a bit of an accident. At the time, natural radioactivity was known to exist at the Earth's surface, coming from minerals like uranium, radium, etc. Hess therefore began a series of balloon ascents in the hope of measuring the falloff in radiation at higher altitudes. Much to his surprise, he found instead that the radiation began to increase at 1 kilometer above sea level. In fact, at 5 kilometers, it was several times greater than at sea level. He concluded that this radiation could only come from outer space, hence the name cosmic rays. Hess even made an ascent during a solar eclipse to see if the sun was the source. It wasn't. The source is still not known, but we do know that cosmic rays consist mostly of atomic nuclei with very high energy that sometimes disintegrate and produce the showers that Yukawa referred to. Cosmic rays are believed to be responsible for Darwinian mutation, computer crashes, and cancer, and for a while they served as the physicists' nuclear physics laboratory. False validation. It only took 2 years for Yukawa's prediction to be verified, less than for Einstein's prediction, or at least so it seemed at the time. In 1936, a particle was observed in cosmic rays with a mass close to Yukawa's prediction, and with electric charge. The excitement in the physics community was immense. But the bubble burst when it was discovered that the new particle did not interact appreciably with nucleons, the sine qua non for nuclear force field. This caused Isidore Rabi, 1944 Nobel laureate, to exclaim, "Who ordered that?" True validation. The dilemma was resolved 10 years later thanks to an improvement in detecting cosmic rays made by Cecil Powell, an English physicist. Powell's idea was to record radiation tracks in a photographic emulsion rather than in the previously used cloud chambers. Powell collected data from a number of high-altitude sites, including the French Pyrenees and Bolivian Andes. In 1947, he found tracks made by a particle with a mass not much different from the meson discovered in 1936, but that interacted with nucleons, as Yukawa had predicted. Yukawa was awarded the 1949 Nobel Prize, and Powell's followed a year later. Two mesons. When Einstein asked why he didn't use shaving cream, he replied, "Two subs, that's too complicated." Physicists had a similar problem with two mesons. To minimize confusion, Powell added Greek letter prefixes, called the 1936 particle a mu meson and this 1947 particle a pi meson, later shortened to a muon and pion. When the pion was recognized as the Yukawa meson, the muon became a kind of orphan child. It didn't fit any theory. The story eventually had a happy ending when the muon found its place in quantum field theory as a kind of fat sibling of the electron. Yukawa's error. Despite Yukawa's great success, he got one detail wrong. His mistake had to do with the mathematical difference between scalar and pseudoscalar fields. Even to define these terms would take us beyond the scope of this book, but the difference was serious enough to create discrepancies between his theory and later experimental results. The difficulty was resolved in 1941 by Julian Schwinger and William Rarita, who showed that the strong field is in fact a pseudoscalar. This paper was published when Schwinger was 23 years old. Quarks. I would like very much to leave the subject at this point, with the Yukawa field and its pion proving a great success. However, a major change in our understanding of the fundamental fields occurred in the 1960s as more quanta of the strong field and the nucleon field were discovered, in fact an embarrassingly large number. This led to a variation of quantum field theory called quantum chromodynamics, in which the strong field is composed of more basic fields called quarks and gluons, even though these basic fields are never seen. See the invisible quark in chapter 6. But don't worry, this need not concern any but physicists. Whether it is a basic field or a composite of quark and gluon fields, the behavior of the strong field remains the same.